Hi there, folks. Today we're looking at possible outcomes, and this is going to play into probability a little bit in terms of finding the total number of possibilities for certain things. All right. So far, we've been dealing with really simple things where kind of the number of possibilities is pretty obvious, but now we're going to start getting into some things where the number of possibilities isn't quite given to us. We have to find out what the number of possibilities are through some sort of mathematical process. Okay, so that's what we're looking at when we talk about possible outcomes. And the first thing we're going to look at with possible outcomes is factorials. These will come into play when we start doing things like permutations and combinations. We'll also see them show up as we're finding some of the total number of possibilities today. All right, so a factorial of n is a natural number, so it's one of our counting numbers. Then n factorial, and that's what this little exclamation point symbol means. So that's our factorial symbol in mathematics. So that's n factorial. Basically, it's n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 until we get down to 2 times 1. And you're probably looking at that thinking, well, where in the world did 2 times 1 come from? We were dealing with n. All right. But keep in mind, n is just a number. So when you do n as a number, n minus 1 is basically the number before that. Okay. So if n was a 10, this would literally read as 10 times 9 times 8 times 7 times 6 times 5 all the way down to 1. Okay. So basically, factorials are pretty simple. You start with the number that's given, and you take every number under that and multiply them all together. For example, if I look at something like this guy, it's 8 factorial, which just means I do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And I multiply all those together, which I believe gives me 40,320 if I remember correctly. Okay? The next one, 4 factorial. That's just 4 times 3 times 2 times 1. And that gives me a 24. This one, 6 factorial, that's 6 times 5 times 4 times 3 times 2 times 1, which I believe gives me 720. Okay, and there's also a factorial button on the calculator where you have a scientific calculator or a graphing calculator. It's under the probability section, and you can use that factorial button to do some of these. However, the factorial button will come up short as you try to do some of these things, all right? The factorial button can only go up to a certain amount before the number's too big for the calculator to handle. So we have to be able to understand how to do some of this by hand, all right? If we look at something like this guy, 6 factorial divided by 6 factorial divided by 4 factorial, we already figured out that 6 factorial was 720, and that 4 factorial is 24, and then I could actually do the division there, and I would get 30, okay? But if you think about what's represented here, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, and 4 factorial is 4 times 3 times 2 times 1. Can you see that the 4s are going to cancel, and the 3s and the 2s and the 1s? So all I'm left with is 6 times 5, which is 30. And the question becomes, why would I want to reduce it that way? Well, if you look at this next one, do you really want to do 120 times 119 times 118 all the way down to 1? No. And maybe you're thinking, I'll use the factorial button on my calculator. Not going to work. The calculator can't do that one. The number is too big. The only possible way to do this is to reduce it by hand first. Okay? And really, we don't have to write all of this out, but if you understand that the factorial just starts counting down, I'll just draw a couple of them. And that goes on kind of forever. Same thing here, that's 118, well, not forever, but all the way down to 1. Can you see that the 118s are going to cancel, and the 117s and the 116s and the 150s, basically everything from here on down is going to cancel? You see that I'm left with 120 times 19, which that I can easily do on the calculator. So here on my calculator, I do 120 times 119, and it gives me 14,280. But again, the calculator can't do that. It can't do 120. We have to reduce it by hand first, okay? So that's the idea behind factorial. But now let's start getting into the possibilities here. Oh, and also the 0 factorial. This is a kind of a special case, but 0 factorial is 1. All right. And really, the idea behind factorials, like the idea here is that factorials give us the number of outcomes when we're arranging that many things. So 8 factorial is telling me that if I have 8 things being put in different orders, there are 40,320 ways I can do it. That's why 0 factorial is a 1 is a good way to think about it. If I have 0 things that I'm going to arrange, there's still one way I can do that by arranging nothing. Okay, so let's talk about independent events. Independent events are basically outcomes that don't affect one another. We already know this, but really, again, just like when we were doing this with probabilities, the difference here is just using your imagination to do these things. Okay, so something like this, if we are not using any of the mathematical processes and using factorials and using later what we'll find out is a fundamental counting principle, the only way to kind of come up with the different possibilities is to literally write them out. We call this doing a diagram or a tree diagram. And so like this one, it says a Sandra card offers customers a choice of hamburger, chicken, or fish on either a plain or sesame seed bun. How many different sandwiches are possible? So the way to count up the number of possibilities is literally write out the situation. So I could have a hamburger, chicken, or fish. And so if I chose the hamburger, I could have that on either a plain bun or I could have it on a sesame seed bun. If I chose the chicken, I could have that on a plain bun or I could have it on a sesame seed bun. And if I chose the fish, I could have it on a plain bun or I could have it on a sesame seed bun. Now, I don't want to tell you what to do with your lives, but if a sandwich cart, if some guy's pushing a cart around, often fish sandwiches, that is just a food poisoning waiting to happen, so don't order the fish. But anyway, so here, when I look at this, I have 6 possibilities. I can literally count them. 1, 2, 3, 4, 5, 6. So the answer here is how many different sandwiches are possible? The answer is 6. And hopefully you're looking at that saying, well, Mr. Jansen, there were 3 options for the type of protein, and there were 2 options for the type of bun, and 3 times 2 is a 6. Well, yeah, that's the idea. We want to see that shortcut here. Instead of writing out the different possibilities, that shortcut, 3 times 2 gives us 6. That's the fundamental counting principle, which is the next thing we're going to look at. So the fundamental counting principle says this. It says multiply the number of ways each event can occur, and that will give you the total number of possibilities. All right? So if like the first event was choosing the protein and there were 3 options, and the second event was choosing the bun and there were 2 options, the total number of possibilities would be 3 times 2, which is 6. That's the example we just did. All right? But we just take the number of possibilities for each thing that we have and multiply them out, and that gives us the total number of possibilities, the total number of combinations. All right? For example, if I look at something like this guy, a restaurant offers regular cheese, bacon, and bacon cheeseburgers with a side of fries, chips, or tater tots. How many different meals are possible? So basically, we have to choose a type of burger, and if we count them up, once again, there's 1, 2, 3, 4 options here. So there are 4 options for the burger, and then we look at the sides. There are 1, 2, 3 options for the sides. So the total number of possibilities would be 12. And again, we could make a diagram and say, okay, I could have the regular with the fries, or the regular with the chips, or the regular with the tater tots, or I could have the cheese with the fries and cheese with the chips and cheese with the and I could count out all 12 of those possibilities. But the shortcut here, the fundamental counting principle, just says, hey, there's 4 for this option, 3 for the next option. There's 12 different possibilities that I could make. Okay? If I look at something like this guy, again, same kind of thing. A 4-digit combination lock uses 0 through 9. Any number can be used and repeated. How many different combinations are possible? So we've got our 4-digit combination lock. And we just have to ask ourselves, how many options do I have for the first digit? Well, 0 through 9 is actually 10 options if you count them up. Like 1 through 9 is 9, plus 0, that's 10 options, right? So there's 10 options for the first number. Well, there's still 10 options for the second number. I could make the combination 1, 1, 1, 1. I wouldn't recommend that. Or something like 1, 2, 3, 4 probably wouldn't be a good option. All right. There's 10 options for the third number. There's 10 options for the fourth number. And so to figure out the total number of options, I just multiply these together. And so there are 10,000 different combinations I can make. And that's a lot. When you're thinking about it, one digit numbers and just a 4-digit combination, okay? 10,000 possibilities. Now, again, some of those possibilities are not ones that anybody would really use, like 1, 2, 3, 4 would not be one that you should use. Okay, so if you start eliminating some of those really obvious ones that people shouldn't use, well, that number gets narrowed down a little bit. Okay, and we'll see some of that a little bit later. But dependent events, remember, dependent events are events that do affect one another. When we did this with probability, the big thing was using our imagination. And it's no different here. We just have to use our imaginations, think about the situation, pretend that this thing is playing out. And it makes it pretty obvious what the possibilities left are going to be, so we can find out the total number of options. For example, Mr. Jansen is putting 8 math books on the top shelf. How many different ways can the books be arranged? All right. So again, I've got 8 slots available for my math books. And so I have 8 math books laying here. So I have 8 options for that first slot. So I have 8 options for this one. So let's say I take my Algebra 1 book or my Algebra 2 book and I stick it there, right? Well, now I have less books to choose from. One of the books is already on the shelf. So now I only have 7 books left to choose from. Okay, maybe it's my geometry book. Who knows? All right. But now once I place that second book up there, I only have 6 books left to choose from. And see, as I place books on the shelf, I have less books to choose from. Now I only have 5 books, and then 4, 3, 2, 1. And this should look familiar. This is 8 factorial. See, factorials appear naturally when we're talking about arranging things. And if you remember from the previous page, 8 factorial was 40,320. Okay? This one, again, just using our imaginations a little bit. It says a 4-digit combination lock uses digits 0 through 9. If the combinations cannot start with a 0 and numbers cannot be repeated, how many combinations are possible? So here's my 4 digits. So 0 through 9 is 10 options, but I'm not allowed to start with a 0, so I only have 9 options for the first number. Okay, I can use numbers 1 through 9, so there's 9 options. And then most students here go, oh, that means there's 8 options because you can't repeat the numbers, so there's 8 options for the second one. No, there's still 9 options. And I want you to think about that for a second. So there was 1 through 9. I picked one of those numbers. I'm not allowed to use it again. So now I'm down to 8 options, right? But now I can use 0, so that gives me a 9th option for the second one. See, I wasn't allowed to use 0 at first, but now I am allowed to use 0. So even though I lost an option, I gained one, okay? So you got to really think about the situation. Now, once I use one of those, I only have 8 options left. And once I use another number, I only have 7 options left, okay? So that first value was limited, all right, because I wasn't allowed to use 0. But then I lose the number that I've chosen, but I gain 0 back. That's why it stays as a 9 at first and then counts to an 8 and a 7. So it's kind of looks like a factorial a little bit, but not quite. And this one I don't have memorized. I'm going to have to punch this into a calculator. So I get 4,536. And if you missed how significant of a drop that is, this is the same question that I had earlier when there were 10,000 options, and I only limited it a little bit. I said, hey, you can't start with 0 and you can't repeat numbers. And look at that. I have less than half the options I had previously. Okay, and this is kind of what happens as we start to eliminate some of the obvious types of combinations, like 1 for all 4 of them wouldn't be an option down here. We lose about half of that. And so that's why some of these things, when you look at combination locks and stuff like that, they can be more complicated and they have, more than just single digits. It's because as we start to eliminate some of those obvious choices, it really narrows down, it really takes down a lot of the options that we have. But again, factorials, start with that first number, count down and multiply, all right? And then the fundamental counting principle, how many options do I have for each thing? Multiply them to get the total number of options. All right. And again, just think about the situation and that'll take care of dependent versus independent. All right.